My name is Maxim. I'm the Toolchain tech lead of Linaro Toolchain working group. And today we are going to have several presentations about the Toolchain projects and the Toolchain CI infrastructure that we have built over the last several years. This first session is an overview of the various configurations we are tracking in our testing infrastructure, and subsequent presentations will be on the advanced topics, advanced features of that CI, and what results we are getting from it. So a couple of organizational topics. If you have a question, raise your hand, and someone will get you a mic, and you can ask your question. It's fine to ask the questions during the presentation, but don't be surprised if I don't immediately give you the word. Maybe I'm just wanting to finish the thought that I have. Also, this presentation is a 50-minute one, and it will be structured in two parts. In the first part, we are going to discuss the theory and the design of the system. And in the second part, we will try to do a bit of interactive demo to show how, and we will look at the individual configurations and what value we are getting from those configurations. So if you cannot stay for the second half, it's fine. We will have a 5-minute break, and you can get a coffee or switch to a different session. Okay, let's go. So what are the principles of this CI, and what consequences we have flow from those principles? The main one is that engineering time is precious. We are building CI as a tool for maintainers of open source projects. That is its primary goal. And engineering time of both maintainers and the developers of open source projects is precious. It can be precious because these people are paid quite high salary, or it can be precious because we cannot force volunteers to do the work that they don't want to do. So the output of the CI needs to be very high quality regression reports, which the developer can take and easily understand whether he or she can or cannot solve the problem. Machine time is not precious, but it is limited. We don't have the resources of all the CPU power in the world, yet we want to track a quite big number of configurations. So we need to figure out how to do that. And finally, and this is one of the fundamental constraints for the CI we are building, is that we want to track upstream projects, and we do not control the speed at which those projects move. We need to be able to find problems, even if our single build and test takes 5 or 10 hours, but the project gets 20 or 100 commits or 100 commits every single hour. So if we have those constraints and those desires, this is the immediate consequences that we need to satisfy to build our CI. We want engineers to be notified only about single commit regressions. When there is an email or a report where you list 5 or 10 emails of the developers, each of those 10 people can think that it surely was not my patch which broke this. It was one of those other 9 guys. And you don't get any action from the developers if this happens. Before and after comparisons, test result comparisons are the most interesting if you have results before the patch, immediately before the patch, and results immediately after the patch, and you can compare them side by side. It can be much easier to understand what the problem is, especially in performance-related problems like not a test breaking, but rather benchmark slowing down or benchmark growing in size. And finally, absolute results are useful and interesting, but they are interesting to see the history of what has been happening to a given configuration. They are not as interesting for CI itself. I would say for automated analysis that drives CI. A few disclaimers here. Linaro Toolchain CI is not the same as Linaro CI. There are many other CI efforts at Linaro, and even at our team, we have 3 separate CI efforts. In addition to this one, it is LLVM build bots, which is driven by the upstream build bot infrastructure, and the what we now call legacy CI, which we are gradually phasing out. There is no best CI. Every CI is a tool for a job. This CI was written and created specifically as a tool for upstream maintainers. For other projects, other approaches to CI and other implementations of CI can be better. And finally, that we are toolchain engineers, we are compiler engineers. So our CI has front ends, middle ends, and back ends, just like a compiler. Before we start and go into the details of our CI, let's reflect for a moment on the 2 main CI approaches. I call them the first one, build, build, and build, and the second one, build, reduce, and bisect. An example of the first approach is an LLVM build bot. And many CIs that you get on platforms like GitHub or GitLab. You try to build your project as quickly as you have machine power and test it, and your goal is to reduce the commit range that every single build is covering, ideally to get to single commit ranges. But if your project fundamentally, commit ranges are determined by 2 factors: the speed of your open source project, or the speed of your proprietary project, and the amount of time it takes to do a build. It has some good benefits. It's usually simpler to code, and it fits very well for slow-moving projects when you have maybe 1 commit per hour or less than that. And many open source projects fit into that description. However, if you have a faster-moving project, I would say that the main problem is of the first approach is linear complexity. And in a project where you have tens or hundreds of commits per hour, you get those 10 people or 20 people blamed for every regression, and you don't know who exactly caused the problem. In the second approach, our goal is to build at the pace that we can manage, so maybe 1 build per day or 1 build per week. But if we detect a problem we need the ability to start bisecting and narrow the problem down to the single commit. There is an additional step here. It's not just build and bisect. Reduce step is when we are narrowing down which of the open source projects is responsible for the regression. So who is familiar with the GNU toolchain here? So GNU toolchain consists of the generally 4 or 5 projects, depending on the configuration. It's binutils, which is assembler and linker, GCC compiler, glibc library, and GDB debugger. And you test all those 4 separate projects, 4 separate Git repositories in a single build. You build the whole toolchain, and then you run tests. And when you see a regression in that, in the GNU toolchain, you first need to understand what project caused the regression. 90% of the time or 95% of the time, it will be the compiler, but it can also be the C library, and it can also be the binutils or the debugger. So for every regression, you first need to identify which of the 4 projects caused the problem, and then you bisect down to a single commit inside that single repository. Because we are doing bisection, we get logarithmic complexity, which is nice. Even if you are building once in 3 days, and you get a range of 2,000 commits. 2,000 commits is how many? 11 steps of bisection, which is big, but usually when you are bisecting, you can narrow down the test suite. So when you are building, you're running the whole test suite, and then you see a regression. But usually you can then rerun just only that part of the test suite. So the bisection, individual bisections, tend to be significantly faster. And that also allows us to do bisections on a subset of the tests, which is much, much quicker. So what usually happens is once in 3 days, we build every single configuration that we support if we see a regression in a particular configuration. Then we start bisection. It may run for 10 hours, it may run for a day, but after a day, we get a report which puts the blame for that specific regression on a single commit. And at that point, we send out an email automatically to the patch author saying that, would you please investigate this? This is the data before you patch, after you patch. It seems like a legitimate problem. Unfortunately, if here you can get feedback within a couple of hours of the patch hitting the main line, in this case, sometimes you have to wait for a few days for that feedback to come in. These are the trade-offs. Any questions so far? Admiral?
Is that working? Yeah. If you have multiple regressions in the same build, do you which stage of that pipeline do you split that into multiple instances of reduce and bisect and so on?
Yeah, good question. And when we are detecting a regression, regressions are relative, and we will talk about that in a moment. You always compare it to a baseline. So let's say you have 2 new test failures, but those 2 test failures were caused by 2 different commits. When you start bisection, you will detect last good revision, which has 0 test failures, and then you will detect the first bad commit, which has 1 of those failures. Then we are going to make a report of that, because it's a regression by itself, and we are going to reset the baseline, what are the expected failures, to that first bad commit, and then test tip of the trunk again, and at that point it will again see a regression, but it will now see only 1 failure. It will trigger the whole same pipeline again, but it will start bisection from a different baseline this time, and then it will detect the second regression. And this actually happens quite often, that we get one regression, that we get several regressions in a build, and then we start bisecting them, and it can turn out to be 2 or 3 different commits responsible for these regressions. This whole system was started as a project, as a helper project for building Linux kernel with LLVM. And at that point, like, part of the Linux kernel could be built with LLVM, but not all of it. So what we did, we set up a project that if this commit of LLVM and this commit of Linux kernel can produce 100 object files, then if that number ever goes down, we want to understand what commit caused that number of object files to go down, so that in theory, eventually it will start going up, and we will catch all the cases when it tries to go back down, and we will prevent those, and that's how we will get Linux kernel compiling with LLVM. Okay, that was the overall design and architecture. Now, regressions and metrics. It's important to understand the difference between a regression and a failure. A regression is a new failure that does not appear in the baseline results. And the big thing here is that regressions are always relative. Failures are absolute. You can see in the test results there is a failure or no, not a failure. Regressions are always relative. It depends on the baseline you are comparing to, exactly like in the question that Will asked. As engineers, we are fixing failures. This is what we are paid to do. But as open source maintainers, we always know that there are existing bugs and problems in our projects. And ideally, we want to fix them. But our #1 priority is to avoid our project becoming worse. We want to avoid the regressions as our first maintainership responsibility. And this CI, if you remember one thing from this presentation, this CI is about finding single commit regressions. That's all. The reason why it is single commits is because we as maintainers want to offset as much burden of fixing problems to other people. And single commit regressions have very nice properties. Entirety of the regression can be attributed to a single change. That change has a real human with a real email address, which we can send email to, and we can get in touch with that developer and ask him or her to at least look at the problem and ideally fix it. Because it's single commit regressions, it's hard to ignore via diffusion of responsibility. This is when you send a report to 10 people instead of 1. And finally, it's easy to revert. If everything else fails, and you cannot interest the developer in fixing the problem that his or her patch caused, if the community policy allows it, you can just revert the patch. And it's an easy fix. The next topic is about, so if you have a regression, that automatically implies you have to compare results. You no longer have all green or all red CI, but rather you have CI which can become a little bit better or a little bit worse. The results can become a little bit better or a little bit worse. And to compare CI results, we are using a thing we call metric. Usually it's a number, but really it's just a predicate which is given two results, however they look. It can be two numbers, it can be two test result files with tests passing and failing. It can be performance feedback from Linux perf or from your benchmark. And that predicate just says, yes, there is a regression, or no, there is no regression. And by using this metric, we can fully automatically do the reduction step, the bisection step, and we can generate the report for that specific metric. Okay, how we are doing on time? We have about 5 more minutes, then we'll make a break, and then we will have the second part of this presentation. Every single CI configuration, even it may gather results for several areas like code speed, code size, number of vectorized loops. Every CI loop tracks a single metric. So for example, if we want to detect code size regressions and we want to also detect code speed regressions, we have to have 2 separate loops. And these are some of the metrics that we are using in our CI. Number of successful build steps. This is just how much of the project you can build. New failures in the test results. How many binaries were built. For example, when you are building a distro or an Android, you can detect when before the patch you could build a given component of Android, and after the patch it doesn't build for whatever reason. And number of object files built. This is the very first metric that we have started this project with. And on the benchmarking side, number of CPU cycles. So this is a measure of speed for single-threaded benchmarks. Number of execution second for multi-threaded benchmarks. Code size of binaries. And the last 2 are somewhat specific. Number of vectorized loops. We added these because we did a rather big auto-vectorization project for GCC, and we wanted to make sure that we will catch regressions when our work, or if our work is degraded in the subsequent versions of the compiler. We wanted to protect our investment into the auto-vectorization improvements. And these are the CI projects and CI configs that we track. Let's quickly go through them. 1, 2, 3, 4, 5, 6, 7, 8. So about 300 CI configurations. We are done. Thank you. We have a 5-minute break, and then we are going to look at some of these configurations. Okay, so before we go into a live demo, which can blow up at any minute. Any questions or comments? Use the mic.
Thanks. Just wondering if there's like a third-party tool you're using to check the state of all the projects.
Yes, there is, and we call that dashboard. Dashboard, in our specific case, we are using LNT, which is a dashboard that LLVM project developed. And LNT stands for LLVM Nightly Testing. That dashboard is quite easy to import data into, and it provides good graphs to visualize how the history changes. So it's, while we primarily want to detect regressions and create regression reports, we also want to see what was the state of the project like 6 months ago or a year ago, and make sure that we are trending, the number of failures is trending down rather than trending up.
Yeah, so I was just wondering about kind of the nature of the failing tests, because in my experience, and I usually work with hardware in the test as well, we have tests that kind of flip-flop, which means you won't find this single commit, and after a while you might have 2, 3, or 4 of these failures, and it starts to get a bit hard to work with it. But I assume this is more of like a purely software project, so you might not be so prone to those types of failures.
So you mean like flaky failures?
Yes.
The gentleman standing right next to you will have a very good description of how we deal with that. Okay. And we do have, that was a very, very big problem. And still, well, it was a difficult problem, which we invested quite a lot of time in solving. So even though we are doing compilers, there can be a lot of instability, whether it's in the test suite, or for example, when we do benchmarking, which naturally has, speed benchmarking, which naturally has noise from the hardware and microarchitectural artifacts. So it's very interesting. I'm going to touch on this slightly in this presentation, but I think it's right after this presentation, advanced features. Yes. We are going to discuss more how we handle noise and flaky tests. Okay. So for the next step, I need a random number between 1 and 6. Thiago, who is completely not planted and will give us a real random number. If anyone wants, by the way, to provide his or her own random number, raise your hand and you will be picked. Yes? 4. So we are going to look at the code at the benchmarking. So yeah, this is the most demo unfriendly topic. So we are going to the benchmarking slide, this one. Now I need a number between 1 and 11. 5. Yeah. 9. Code vectorization. This will not be very interesting because this is still in development, but okay, we'll try that. Finally, we need a few numbers here. So between 1 and 2. So that will be vectorization for LLVM architecture. ARC64. Compilation flags. 03. Or OS. OS. Vectorization for OS is disabled, so we are not going to get anything interesting there. So it's either, I'm guessing for vectorization, the only valid value here is 03, and LTO or no LTO. LTO is link time optimizations. No LTO. So this gives you an idea of how many configurations we are tracking. So vectorization for SPEC 2017, LLVM? LLVM, ARC64, 03, non-LTL. Let's try and see. Where do we start? Where do we start? Okay, that's 2017, fast, /LLVM. Huh. Code vect. Okay, so this is GNU. This is GNU. This is still GNU. This is LLVM 32-bit ARM. Code vect. This is SPEC 2006. Why don't we have it for LLVM? Oh, here it is. So this is LTO, this is non-LTO. Vectorization, SPEC 20, well, it's not SPEC 2017 fast, it's SPEC 2017 rate, which is almost the same thing.
It's GNU. The one you want is above, I think.
Oh, I think for LVM. We don't have vectorization tracking implemented. We have it implemented for some of the configurations. So I think this one is the closest one. It's SPEC 2006, LLVM AR64, 03. So here, these are the builds on the left, and they are here. You can see regressed by having 12 vectorized loops to none. So a particular function in one of the benchmarks was now lacks 14 vectorized loops. Let's see if that resulted in a regression report. Email subject reduced by 50% on WRF. Yes, so not quite clear. So yeah, this configuration is not stable yet. So we will not get a good regression report from here. Let's try another one. Where is the presentation? Again, number between 1 and 6. Again, number between 1 and 6. 2? Cool. Now, also between 1 and 6? 4. GCC check. Yes. Architecture? ARC64. No one is interested in 32-bit ARM. Okay, next one will be 32-bit ARM. And this is only for the bootstrap. So this is only for if it was selected 3. So GCC check for 64-bit ARM. That one is a production quality configuration which we are getting a lot of value from. So this will be more interesting. Here is So first of all, this is what I get in my mailbox. This is for a 32-bit ARM, but this is just an example that, dear contributor, your specific patch after your patch we have, which is a patch in GCC, not STS, right? Now in the GDB test suite, after this GCC patch, we are seeing 3 new failures. How awesome is this? A developer who is working on GCC will run GCC test suite as part of the development process, but they are unlikely to run glibc or binutils or GDB tests yet. And the most difficult bugs are we get when you get interactions between the several components in the toolchain. So when a GCC patch causes a problem in glibc, or we had a glibc patch which has caused a problem for GCC vectorization. I would never imagine that until we got an actual report, which we got only because this is fully automated and it runs every day, and we get this kind of reports. So, and this is what the email report looks like. And this is Jira card, where every single report is created as a Jira. No, this is the wrong one. Yeah. Every single report we have as a Jira card here. So this GCC commit caused 1 failure, 1 regression. This is 3 regressions, and so on. And even though you can see this is the GCC 15, which has just started development cycle, about 1 in 30 commits, like 15, commit 15 from starting of the development cycle, commits 59, we get regressions, especially at the beginning of the development cycle, quite often. This is end of GCC 14 development cycle. Look how many regressions we have detected in the last, let's say, a year. This system has been running for about 9-10 months, and this is how many problems we have detected and notified developers. This is a huge list. And also let's look at what, and the process is, we detect a problem, and the same regression can cause the problem in many similar configurations, right? So we have for ARC64 check bootstrap LTO. So this one has caused the regression in every single, well, not in most of the ARC64 configurations. We have an engineer assigned to following up on this regression. So this is a member of our team who will contact the patch author and make sure that this problem is fixed in one way or the other. This is the first interesting point to look at. And then, let's see. So this is the LNT dashboard. Let's look at the status of ARC64, correct? There is a lot of data, but the interesting ones are total fails and total flaky and number of all tests. Let's look at this. How does this look? So-so. So let's look at the here first. This is the total number of tests in the test suite. This point here is May, a year ago. Actually, it's a year ago almost to a day, 16th of May. And the total number of tests is relatively stable, so it can decrease a bit or increase depending on the configuration changing. For example, here, we have enabled Ada and Objective-C and D language test suites. So just the number of total tests increased. It's not as interesting as the number of failures. So this may not look interesting because we have a couple of outliers here. But if we just look at this part, these are the number of failures in a given run. So for example, every single increase here corresponds to a regression. And more than just a regression, it is a single commit regression. And we have a link to the card explaining what has happened here. Again, with a specific commit responsible for every single one. For this jump, for this jump, right? It's just an additional one failure in the test suite. When you are looking at the compiler test results, which is like 900,000 tests, and you have one additional failure created by Andrea, who conveniently left the room to go into another meeting. Well, in this case, it's 10 regressions. But even one regression, for every single new failure, we have that accounted in this dashboard. The reason why for the first half, here we have a very turbulent change, and for the second half, it's quite smooth. It's because this history is compressed. This is history for the last 2 months, and this is the history for the 10 months. So we, to not have too many data points, we just cut the parts where we don't have any change from the results. That's why it looks so turbulent. So every time we are doing a new build now, and we add a point here, we also remove a point here to make this, to be able to have multi-year history fit on a single graph. But still, so that we know exactly when there is a change in the current, so for example, from going from this point to this point, we have a regression report as a Jira card. And then from this point, 46 failures down to 48 failures, again, we have a regression card. This dashboard, even though it has number of failures, it looks the same for performance when you have benchmarks slowing down, or when you have code size growing up, or Linux kernel object files increasing or decreasing. Cool. I think this is everything I wanted to show on the, one more thing. Right, about the flaky tests. So this is number of failures. And this is the number of flaky tests we have in our test suite. Number of flaky entries. So we automatically detect when a test is flaky. How it's done will be discussed in the next presentation. But the point is that we have an automated list generated from the results where when we see that the test behaves as a pass in one build and then as a failure in the build with the same exact compiler, we mark it as flaky and we ignore it in the results. And generally, we want to see the number of flaky entries trending down. So we had some problem in this area where the number of flaky tests shot to 300. But then it was a test suite problem, it was fixed, and we returned first to about 10 flaky tests. And at the moment, I believe we have 0 flaky entries for ARX64 GCC testing. Number of flaky tests for GDB 32-bit testing is very different because the debugger testing is a whole another beast. Cool. Any questions on this?
Hi. So like my colleague said, we work a lot with hardware, and that's sort of the noise of our flakiness and randomness. But how do you get, what's the source of noise to cause flakiness in a pure software project? Do you know, or have you?
There are several sources. So in terms of test flakiness. Christoph, actually, maybe you want to cover that.
Yes, we have observed several causes for that. Thiago, you will give more details in a few minutes. Yes, there are some problems in the test case themselves, for instance. It can also be in the test harness. For instance, we have already found bugs in GNU. We also noticed issues with GDB starting thousands of processes, leading to random crashes everywhere. So there are several classes of reason for flakiness.
For example, if we are testing using QEMU, there can be a flaky test. So if there is some slightly undefined behavior in the kernel, it can cause a flaky test.
What's the time overhead in so you have your Jira ticket list for the detected regressions? You report them to the person who wrote the commit. What time? I guess what criteria do you have for closing those tickets, and where does the work stop and you hand it back to the author, kind of thing?
We have 3 main criteria for closing. We have 1 main criteria for closing a Jira ticket, and that criteria is this regression is no longer our problem. And we achieve that by a couple of things. First, email is automatically sent out to the patch author at the same time when the Jira ticket is created. And in the email, we ask, would you please let us know if you are working on this or if you are fixing this? If the patch author confirmed that he or she is working on the fix, whether or not it's done or committed, just they are interested in the problem, we close the Jira ticket. If we see that this problem is easy to fix, it's a typo in the test case, we fix it ourselves. Or if it's not trivial to fix for us and the patch author is not responsive, we create a bug report in the upstream Bugzilla. At that point, it becomes a problem of the community, and we close the Jira ticket. And then we work on that bug report with our upstream hats on. Okay, we have like 1 or 2 more minutes. Let me quickly show you benchmarking dashboard and benchmarking. Oh, where is it? Where is it? This one. So these are reports for the benchmark, for the benchmarking configurations that we have. And here we get reports like this commit slowed, this is SPEC 2017 and SPEC 2006 benchmarks. This commit has slowed down this particular benchmark by this number. Or it has increased code size of this benchmark by this number. And for example, even though here it's a very short summary, in reality, it can be several benchmarks regressed by the same commit. It's just we pick the benchmark with the worst regression and put it into the title. In this case, only at -03, commit causes a regression in one of the 25 benchmarks. And that regression does not appear if LTO is enabled. It doesn't appear on 32-bit ARM. It doesn't appear when O2 optimizations are enabled. So it's a problem in a very, very specific configuration, and we catch it. There are commits which can reduce performance across the table, like in both O2 and O3, both for ARC64 and ARC32. And such commits are most important for us to fix. This system allows us to gather for each commit of interest a list of configurations it has regressed. And then we prioritize investigating performance regressions that affect the biggest number of configurations. So a commit which has caused 5% regression across everything is more important to fix than a commit which has caused a 20% regression on one benchmark in one particular configuration. And let's see if I can, so for example, that was O3. Let's see if we have, so that was photonic, right? Photonic. Here it is. Where is photonic? Somewhere at the end. And the Z percentage. This is performance graph of that benchmark. And I'm guessing, yeah, this is the regression, right? That we have seen. The link is broken, but I think it's the exact same regression that we have seen here. Performance of this benchmark was fluctuating a bit right here, and that's normal benchmarking noise. Then it increased, which is good. No, actually this is, this increase is bad, so this is another regression. Yeah, which we have detected here. This is another regression. Then things improved even to what they, better than they were before, but then unfortunately they have regressed here. So if you are looking just at these 2 points, let's say this is GCC 13 release and this is GCC 14 release, you will see a regression from here to here, and it will be like 10%. But you will not know that actually there was a point where performance was so much better than this. And you can, in theory, if you fix this problem, you can go here. And this will be a huge benefit to the community and to the ARM ecosystem. By preventing regressions, we are claiming back performance improvement. And in my view, it is much easier to get performance improvements from preventing regressions rather than by writing compiler optimizations. This is one benchmark. And this is another benchmark. This is XZ. So XZ, there was a problem here, but in generally XZ is in good shape. So from this graph, we can see that XZ is not something we need to focus on, but photonic is definitely a problem which should be investigated. And finally, an interesting point about benchmarking is when you have noise in benchmarking. And these are variability of the benchmarks that we use to detect regressions. So the scale is on the right, and this is XZ variability. XZ is a very stable benchmark. It changes under 0.5%. If you run the same binary on the same machine under the same conditions, you will see performance measurements within 0.5%. But photonic can, noise of photonic can go up to 1 and 1.7%. And we are generating these variability ranges or variability thresholds automatically, so that we can equally well track benchmarks which are noisy and which are stable. And for a noisy benchmark, for example, for us to detect a regression in photonic, that change, that negative change, has to be 1.7 multiplied by 2, I think, so about 3%. If the regression is 2%, we will not detect it. But if the regression is 5, 10%, we will catch it. For XZ, on the other hand, because its variability is smaller, if a regression is 1%, we will catch it. Thank you. What are your questions?
So this is a really good tool. So a question that I have is, right now it's mainly for the upstream projects, right? Do you even offer this tool, let's say, to companies, let's say they want to do it for their, proprietary projects or something like that, so that at least the concept and all of this can be leveraged? Yes, this talk is just a marketing material. Come talk to me after the talk. Okay, thank you. We built this as a tool for maintainers, but we do realize that it is a quite powerful and interesting tool, and we are offering it as a service.
So I guess for performance benchmarking, you need a platform, right? You need a kernel, the operating system, and all the other components.
Yes.
So with time, you will upgrade, or the platform will change quite a bit. So how does kind of the value of previous benchmarks lose value over time when the platform changes?
We will, when we upgrade the system, the first run on the new system may be a regression compared to the previous results, or a progression. If it is a regression, let's say we have slowed down the system just by reducing the clock rate. We will try to bisect it. Bisection, we'll see that, sorry, I cannot reproduce this problem because I'm getting the same results for the baseline commit and for the current commit. So I will just going to force update of the baseline.
Right.
And at that point, the graph will change. So it will go up, go down. But then again, we are interested in regressions. And after that point, any regression we will detect on the new setup of the hardware.
Yeah, that makes sense. Mm.
And similarly for the noise, by the way, for example, a benchmark can be noisy for whatever reason. Maybe we did not set up our hardware properly. So we can see a lot of noise here, but maybe then we have fixed our configuration of the hardware, disabled network access, or installed a better kernel, which behaves more stably, and the noise goes down. So our noise, so these are the noise points which were used for that specific build. For the next build, it can be different. And you can see that we are always trying to use less and less noise until possible. Every jump in the noise tolerance corresponds to a run where the binary is the same. We have those runs injected into our build system, which are trying to reproduce the same baseline results. And if we see that the binary is same here and the same here, but we see performance difference of 2% between the points which correspond to the same exact benchmark, to the same exact binary of the benchmark, we say then the noise must be this 2%. So we increase it to this point. Then again, we try to decrease it, decrease it. So even if behavior changes in the future, our system will adapt. I thank you for your time. There will be more presentations on the toolchain CI topic, both for the test suite and for benchmarking in this room today. And they will cover these items in greater detail. This was just an overview. Thank you.